AQA A-level physics for the electronics option. We're going to look at some other discrete semiconductor devices. In the last video in this playlist, we looked at MOSFETs, and here are some other devices which we need to know a little bit about. Okay, it's nowhere near as heavy going as the last video. So, what is a diode, first of all? Well, a diode only lets current flow one way, and it lets current flow if it's forward biased. So this power supply is trying to push the current round this way, anti-clockwise in this circuit, and this diode, as it is there, is forward biased. It has a very small resistance, and so the current will flow. Now, if we swap the diode round the other way, then there will be almost no current. So the power supply is trying to push the current round that way, but basically it can't because my reverse biased diode has a very big resistance. Now, what will happen if we make the voltage across this diode big enough, then it will break down. So the breakdown voltage, it depends on the diode. It's usually quite large, but it's unpredictable. You can't always predict when this diode will break down and start conducting. Okay, and the diode is likely to be damaged when it breaks down. So forward biased, you need about 0.7 volts for it to conduct. Reverse biased, when this voltage gets quite large, maybe 20-30 volts, then it breaks down and you get this unpredictable breakdown. Current starts to flow. This corner bit here is called the knee on the curve for obvious reasons. Now, a Zener diode, or a Zener diode if you like, is actually designed to break down. But it breaks down at a certain voltage. It's reverse biased. Zener diode is designed to break down at a certain voltage. For example, this one here is designed to actually break down at 5.7 volts. So it starts to conduct at 5.7 volts. You see there's a little bit of leakage current. Okay, so when it does break down, then the voltage across the diode stays the same. It will stay at 5.7 volts. And the diode will be in series with a resistor. And if we increase the voltage across both of them, the voltage across the diode stays the same. The voltage across the resistor will get bigger. Okay, so in reverse mode, there will be a leakage current before breakdown. You see there's a little bit of leakage current, and the maximum leakage current will depend on the resistor that's in series with the diode. So looking at this, there's my Zener diode in series with a resistor, and you'll see my power supply V in, and we're increasing the voltage. And as we increase the voltage, in this particular case at 5.6 volts, it breaks down and it starts to conduct. Okay, and then when it starts to conduct, the voltage across the diode stays at 5.6 volts. The voltage across the resistor will get bigger. Uses of Zener diodes, voltage regulators. If you want to stop a voltage going above a certain value, which might be to protect some kind of a device. If the voltage across something goes above something, the device will be damaged. Then you could put a Zener diode in parallel with the input. To provide a reference voltage, when we look at op-amp circuits, we'll see how in something called a comparator, a reference voltage is very useful. Okay, our next component is a photodiode. Now, an LED, we know, changes electricity into light energy. A photodiode does the opposite. It changes light energy into electricity. We don't need to know what's happening inside the photodiode, but the photoelectric effect is involved, and I'm sure you remember what that is. Looking at this graph here, my photodiode is reverse biased, and as it's reverse biased, looking at this graph, as we increase the light intensity, yes, the current increases. So the reverse current in milliamps increases as we increase the light intensity. There'll be a little bit of a dark current, yes, but then as it gets brighter and brighter, its resistance gets less and it will produce this current. And again, there's various circuits. I'm not going to talk too much about this because we'll do op amps later on. But here's an op amp being used as an inverting amplifier, and the voltage produced will be proportional to the light intensity. So one use of a photodiode is with a scintillator. Now, what is a scintillator? If some type of ionizing radiation, for example, alpha, beta, gamma or X-rays, falls on a scintillator, then it produces little flashes of light. So if you combine a scintillator with a photodiode, then you've got a detector for this radiation. So some kind of a radiation detector, or in airports, baggage inspection, looking for stuff. You shine X-rays on it. There's a scintillator, produces flashes of light, and then photodiodes will detect these flashes and produce an image. Okay, so this is the last of our discrete devices, and it is a Hall effect sensor. Now, the Hall effect it's all to do with static magnetic fields, and this sensor detects static magnetic fields, not your sinusoidal magnetic fields. When you did kind of magnetic fields and transformers and stuff, you used something called a search coil, which was like a coil of wire which acted like a little transformer. This is for static magnetic fields which aren't moving. We don't need to know how the Hall effect actually works. One thing you do need to know is that the axis of the field and the plane of the sensor have to be the same. So if you look at the chip there, that's my Hall effect chip, and the magnetic field is going through the plane of the chip. If my magnetic field came in that way, then you wouldn't get a voltage. This is my voltage here. So the field must go through the plane of the chip to produce a voltage. Now, some uses for them, which are mentioned in the specification: an attitude sensor. So an attitude sensor is basically like which way is north, which way is south, but also which way is up. So X, Y, Z. And how does it know X, Y, Z? By looking at the strength of the Earth's magnetic field. Okay, it can figure out which way, once it's calibrated, it can figure out which way is X, Y, and Z, which way is up, down, and north and south. Okay, things like a drone or an aeroplane or maybe even a satellite would have some kind of an attitude sensor which has a Hall probe in the X and Y and Z directions. Also mentioned, and I've seen this on a past paper, is a tachometer, which measures the speed of a vehicle. And if you look at the diagram, I think it's pretty obvious how it works. Thanks for watching.